Let's do some problems on computing splitting fields and the degree of the splitting field over the base field. So here's the first problem. So compute or find the splitting field, of the polynomial, f of x equals x to the p minus 1, okay, where p is now a prime, and I sort of want you to find the splitting field of this polynomial over the base field, which is the field of rational numbers. Okay, so let's recall what the definition of the splitting field was, or how one could find the splitting field of a polynomial. So let's recall. So what are we supposed to do here? So take Q, the base field. Now in this case, there is this convenient field, the field of complex numbers on top of Q, which is algebraically closed. So any polynomial has all its roots in C. So what we could do is just take this polynomial f of x. So what are its roots in C? So f of x equals x to the p minus 1 has complex roots. Well, what are they? They are 1. So let me call this zeta, zeta square, and so on till zeta to the p minus 1, where zeta is what we would call the primitive pth root of unity. So it's e to the 2 pi I over p. Okay, so if you think in terms of the complex plane, so this is just, so this is on the unit circle, and look at this angle here, which is 2 pi divided by p. So you are dividing the circle into p equal sectors, and this number here on the unit circle in the complex plane is what we would call zeta. It's e to the 2 pi I over p. Okay, so these are the roots, and then how is the splitting field itself formed? So recall, let K denote the splitting field, which I abbreviate to SF. The splitting field of f of x is, well, take Q and you adjoin to it all the roots of this polynomial. Okay, so look at 1 zeta, zeta square till zeta to the p minus 1. Okay, so I need to take the subfield of C, which is generated by Q and the roots of this polynomial f. Okay, but observe, of course, when you adjoin elements, some of those elements don't really need to be adjoined. You don't get a new field. For example, if I adjoin the root 1 to the base field Q, I don't get anything new. That's just Q again, because 1 belongs to the base field. And well, so I don't really need to adjoin 1. So I could just adjoin the next guy, which is zeta. But observe that as soon as you adjoin zeta, then of course Q of zeta is a field, and because it's a field and zeta belongs to it, automatically zeta square, zeta cubed, and so on, all powers of zeta automatically belong to this field. Okay, so observe that because all powers of zeta power k are automatically inside this field Q zeta. This is for all k, in fact, for all k greater than or equal to 0. Okay, so we understand what the splitting field is. You can just get it by adjoining a single element to Q. That element is just the complex number e to the 2 pi I by p. Okay, now of course I want to understand what the degree of this extension is. So you have seen this before. So this is what we call the cyclotomic extension. So Q zeta over Q, and observe this has degree. So recall from your earlier lectures on cyclotomic extensions that this has degree equal to p minus 1. And why was this? Because the minimal polynomial, or the irreducible polynomial, the minimal polynomial that zeta satisfies, so minimal polynomial of zeta over Q is just the polynomial x to the p minus 1 plus x to the p minus 2 plus dot 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 till 1. Okay, so and recall this one showed that this was irreducible. So again, this is an irreducible polynomial in Qx, and to establish this, one used this important thing called the Eisenstein criterion, by the Eisenstein criterion. And it involved a little bit more. One had to sort of replace x by x plus 1 and do little trickery there, but anyway, it came from the Eisenstein criterion. Okay, good. So that's the first problem. What it says is that the splitting field of the polynomial x to the p minus 1 is the cyclotomic field q of zeta, and it has degree p minus 1. Okay. So recall, of course, the general fact we showed, the general upper bound we proved was that if I have a polynomial, so let's say this is k, and I have some base field f, and suppose if k is so recall our upper bound, k is the splitting field of some polynomial fx in fx, means that the degree of k over f, as we had shown already, is at most d factorial, where d is the degree of this polynomial f of x. So in this particular example, it's at most p factorial, okay, but in reality it's much smaller, okay, which is actually just p minus 1. Okay, let's move on to the second problem. So again, let's compute the splitting field. So let's again take the base field to be q, and let's ask find the splitting field, find the degree, in fact, of k over the base field q, where what is k? K is just the splitting field of the polynomial x to the 4 plus x square plus 1. Okay, so I have k over q, and I've told you what k is. It's a splitting field of a 4th degree polynomial. Of course, the degree, therefore, our upper bound says that kq can be at most 4 factorial, which is 24. Okay, but like we saw in the earlier example, in practice this is often much smaller. So let's see what it is in this particular example. Okay, so again, like we did in the earlier problem, we proceed similarly. We first take q, and to it we adjoin all the complex roots of this polynomial. So let's call this polynomial f of x. So we'll recall that I have c on top, and so I can just think of k as q adjoined all the roots of this polynomial, okay, the roots, the complex roots of this polynomial fx. So let's try and find out what the roots look like. So firstly, f of x is x to the 4 plus x square plus 1. So I need to solve the following equation: x to the 4 plus x square plus 1 equals 0. To find the roots. So of course it's easier to just put y equals x square and solve the equation y square plus y plus 1 is 0. Okay, so this is just we know the solution to this. These are the cube roots of unity. So this is y is just what we would usually write as omega and omega square. So let me just write them out explicitly: e to the 2 pi I by 3 and e to the 4 pi I by 3. Okay, so these are the two cube roots of unity other than 1 itself. So this is my complex plane. So omega is this fellow here, which makes a 120 degree angle, e to the 2 pi I by 3. Omega square is the other root, e to the 4 pi I by 3. Okay, and of course this is what y is. So x, since x square is y, so how do I compute x from here? Well, x is just the square root of y, right? X is just, well, there will be two possible square roots. So I need to say, let's compute e to the 2 pi I by 3. So let me say x is like plus minus the square root of y, if you wish. And here y is just e to the 2 pi I by 3. So I pick one square root, which is therefore, so what are my solutions for x? it is the square root of 2 pi I by 3 is just pi I by 3. So it's plus minus pi I by 3 plus minus 4 pi I by 3, square root is 2 pi I by 3. So I take plus minus 2 pi I by 3. Okay, so let's also locate these roots on the diagram. So e to the 2 pi I by 3, the square root is sort of something which makes half the angle. So this is e to the pi I by 3. E to the minus pi I by 3, minus e to the pi I by 3 is just the thing on the other end of the diagram. I mean, it's just diametrically opposite. So this is actually the same as e to the 4 pi I by 3. Okay, so x equals minus e to the pi I by 3. So that minus I can just think of as e to the 4 pi I by 3. Okay, and similarly e to the 2 pi I by 3 is this point, and negative of that is just something on the other end. So what is this going to be? This is just going to be, so let's see, this is 1, 2, this is 4 and 5. So 5 pi I by 3. So what are these really? Well, you can see these are nothing but the sixth roots of unity. So what are the sixth roots of unity? There should be 6 of them in all. So there are 2 more, that's plus 1 and minus 1. Okay, so if I add in those 2 points as well, then observe that these 6 points that I have, the 2 green and the 4 reds, they are the 6th roots of unity, because the angle between each of them is a 60-degree angle here. Okay. Okay, so where are we? Let's give this a name. So I'll just call this very first guy something. So let's call that very first root. So that is e to the pi I by 3, okay, or the same as e to the 2 pi I by 6, forms a 60-degree angle. So this is, let's call it eta. Therefore the other roots, so what are the choices? What are the roots? X is eta square, eta cube isn't there, instead eta to the 4 and eta to the 5. So those are these 4 guys. The 4 roots that I have here are just eta square, eta power 4 and eta power 5. Okay, as you can see directly. Okay, now what is q of eta? So let's see. So what is the splitting field? So therefore k is just, I need to take q and I need to adjoin these 4 roots, but as we saw in the earlier example, we don't need to adjoin all of them. If you adjoin eta, then you automatically get the rest. Okay, because powers of eta are definitely in this field. Okay, so now the question finally is, so we understand what the splitting field looks like. You just take k and adjoin a single element, just e to the pi I by 3 to q. But the question is, what's the degree of this extension? Okay, in other words, so k over q, so then observe the degree of this extension, is just nothing but the degree of the minimal polynomial that eta satisfies. So this is just the degree of the minimal polynomial of eta over the rational numbers. So let's see, what is this minimal polynomial that eta satisfies? So what are these 4 roots, eta square and so on? They were roots of which polynomial? Well, it was, let's go back to the original polynomial, x to the 4 plus x square plus 1. So of course eta satisfies this polynomial, right? It was a root of this polynomial. But is this polynomial irreducible? That's the first thing we need to ask ourselves. Is x to the 4 plus x square plus 1 irreducible? Well, one has to sort of play with it a little bit to see what can be done to it, but if you sort of use a little manipulation, so here's something you can do, x to the 4 plus 2x square plus 1 minus an x square. Okay, and now this is just x square plus 1 the whole square minus x square, and now I use the identity, so that's a square minus b square, so that's a plus b into a minus b. Okay, so in fact this factorizes into a product of these two elements. Okay, now each of these factors is sort of familiar. So what are the roots of x square plus x plus 1 equal to 0? Well, those are just the cube roots of unity, right? So we know the roots of this. So I should say, so maybe let's just go to the next slide. So observe now, x square plus x plus 1, its roots are the cube roots of unity. So which in our figure, what were they? So that this guy was called eta, this fellow was called eta square, eta to the 4 and eta to the 5. So the cube roots of unity were these two fellows, eta square and eta to the 4. Okay, and x square minus x plus 1 is 0. Well, its roots are just the negatives of these guys, because observe the bottom polynomial is just obtained from the one on the top by replacing x by minus x. So the roots of this are the negatives. Okay, and well, what's that? That's just the other two roots, eta and eta to the 5. So these two fellows are the roots of the other polynomial. Okay, so in fact we now know what the minimal polynomial of eta is. So observe that the minimal polynomial of eta, so eta satisfies this polynomial, x square minus x plus 1 is 0. So this is this x square minus x plus 1. So this is a minimal polynomial over Q. Okay, and it's easy to see it's irreducible, right? You can't factor it any further. Well, just because the roots are not rational numbers. Okay, so therefore this has degree 2. Okay, so what does that mean? That well, this extension k over q that we were looking at, k is q of eta, this has degree 2. So recall, to start with we said it's at most degree 4 factorial, which is 24, but it turns out that it's actually much smaller. It's just a simple quadratic extension. Okay, so let's move on to the next problem. So this is problem 3, which is to compute again splitting field, but slightly harder one this time. So let's take my polynomial f of x to be the polynomial x to the 6 minus 18. Okay, and now again I ask the same question. Let k be its splitting field of f of x over q. Find the degree of the extension. Okay, so let's do this. So let's rewrite it as follows. I'll pull the 18 out, write it as x to the 6 by 18 minus 1. Okay, and let me just call the first term as y to the 6. So let's do one thing. So I mean, clearly there is an obvious root of this polynomial that I can write out, which is just the 6th root of 18. Okay, it's a real root. So let alpha denote that real root, the 6th root of 18, and therefore, okay, let me also change variables. So let me call y as x by alpha. So then observe that f of x can be rewritten as follows. It was 18 times y to the 6 minus 1. Okay, so I have changed variables to y, and now it has this nice form. So now let me think of my polynomial as a polynomial in y rather than a polynomial in x. So to start with, I had this. Okay, so let me find its roots. Okay, well, what are its roots? Well, this polynomial has the obvious roots, which are the sixth roots of unity. So y is just 1. So I'll just use the notation of the previous problem, which is, I'll call it eta. Eta is the 6th root, eta to the 4, eta to the 5. Okay, where eta just denotes the 6th root of unity. Okay, so same notation as the previous problem. So therefore, what is x? Well, x is just alpha times these possibilities, right? So the roots x are just alpha times the 6th root of unity, alpha times cubed 4 and 5. So these are the sixth roots of, these are the 6 roots of this polynomial f of x. Therefore, as before, what's the splitting field? I just take k, I take q and adjoin to it these 6 fellows, alpha eta, alpha eta square and so on till alpha eta to the 5. And observe as before that, well, I have to adjoin alpha definitely because alpha is not in Q. Okay, so observe, quick observation here, observe that alpha is not in Q. Okay, the 6th root of 18 is, well, what is alpha? Alpha is just the 6th root of 18. So what is the 6th root of 18? Well, I mean, one has to just show this is not a rational number. Okay, so I will leave that as an exercise. Similar to showing, for example, that square root of 2 is irrational and so on. Similarly, you can show that this is not rational. Now, so definitely I have to adjoin alpha at least. Okay, so I take Q, and when I adjoin alpha, I get something strictly more than Q, a bigger field. And now, of course, I need to adjoin the next guy, which is alpha eta. But adjoining alpha eta is the same as just adjoining eta itself. Okay, because alpha is already there. So I can multiply alpha eta by alpha inverse, and so if I adjoin alpha and alpha eta, that also means that eta belongs to the adjunction. Okay, so observe that Q alpha comma alpha eta is actually the same as Q of alpha adjoin eta. Okay, and once I have eta, then, well, I don't need to adjoin any further roots, because once I have alpha and eta, I have alpha eta square, alpha eta cubed. Every one of those other roots already belongs to this this extension Q alpha comma eta. Okay, therefore I have understood what my splitting field looks like. It's obtained by adjoining alpha and eta. So now we need to understand how to find the degree of this extension. Okay, so let's do it in 2 steps using our what we know about degrees of towers of extensions. So I will think of this as my tower of extensions. So first step, what's the degree of the bottommost step of the tower? So what's the degree of this? Well, I'm adjoining a single element alpha. So the degree of this extension, as you have seen before, is just nothing but the degree of the minimal polynomial of alpha over Q. So what is the minimal polynomial that alpha satisfies? Well, observe, alpha certainly satisfies the original polynomial, right? X to the 6 minus 18. Okay, so this is certainly one possibility. So I claim this is the minimal polynomial. Of alpha over Q. Okay, why is this? Well, all I have to show is that this polynomial is irreducible. Okay, because I already know that alpha is, I already know that alpha satisfies this polynomial, is the root of this polynomial. Okay, so proof, just need to show this is irreducible. So x to the 6 minus 18 I claim is irreducible by a simple application of, well, the Eisenstein's criterion. So let's apply the Eisenstein's criterion as follows. So observe, all coefficients are zeros, 0x square, 0x minus 18. And what does the Eisenstein's criterion tell us? It says, so let's recall Eisenstein criterion. It says if you can find a prime p, okay, now in this case I'm going to take the prime p to be 2, which has the following property, that this prime does not divide the leading coefficient. Okay, so this leading coefficient in this case is 1. So this prime doesn't divide the leading coefficient. Okay, so leading coefficient. So that's all right. In this case, that's true. And what's the next condition? The prime should divide all the other coefficients. Okay, all other coefficients should be divisible by p. That's also true because they're all zeros. And the last guy is 18, which is also divisible by 2. Finally, the constant term should not be divisible by p square. Okay, now the constant term is 18, and 18 is not divisible by the square of 2, which is 4. Okay, so all the 3 conditions are satisfied of Eisenstein's criterion. So what this implies in particular is that this polynomial is irreducible. Okay, so therefore x to the 6 minus 18 is irreducible in Qx. Okay, and we are done. So therefore it must be the minimal polynomial of the element alpha. Okay, so done. So what does that mean? At least the first step is done. Q alpha over Q, this extension has degree equal to the degree of the minimal polynomial of alpha over Q, and that degree is just 6. So this is a degree 6 extension. Now let's go back. What did we need? We also need to adjoin a second element, which is eta. Okay, so let's try adjoining eta to this previous extension. So now I want to say I already have Q alpha, and to that I add an additional element eta. I adjoin an additional element. So the question is, what's the degree of this extension? Well, again by the same reasoning, the degree of this extension, so Q alpha adjoined one more element over Q eta is just the degree of the minimal polynomial. So the degree of the minimal polynomial of this new element eta, but the degree, I mean the minimal polynomial is now to be computed over, sorry, what did I, sorry, this should be an alpha. So this minimal polynomial of eta is over the field Q alpha. Okay, so observe it's not over Q, but rather over a bigger field. So I have to be a little careful, see whether I am computing the minimal polynomial over the correct field. Okay, so how does one find the minimal polynomial? Well, one tries to find at least one candidate polynomial. Okay, so what is the candidate polynomial here? So observe what was eta. Eta was just e to the 2 pi I by 6. And recall that from the previous problem, we already know what the minimal polynomial of eta over Q is. Okay, we know this, that the minimal polynomial of eta over Q, meaning with coefficients in Q, was just the polynomial x square minus x plus 1. Okay, so look back on the previous problem, we showed that this is exactly the minimal polynomial of eta over the field Q. Okay, well, what does that mean? That doesn't automatically mean that this is the minimal polynomial of eta over this bigger field Q alpha. Okay, so at least it means the following, that if I just adjoined eta to Q, that would give me a degree 2 extension. Right, so let's think of it like this. I have Q to eta. If I just adjoined it, I would get something of degree 2. Right, that's all this shows in some sense. But I claim that, well, this very same polynomial is also the minimal polynomial of eta over Q alpha. Okay, let's make that claim. The same polynomial x square minus x plus 1 is also the minimal polynomial of this element eta over the base field Q of alpha. Okay, well, proof, at least this polynomial is satisfied by the, I mean this polynomial certainly has coefficients in Q eta. So observe this polynomial certainly Q alpha of x. Okay, its coefficients come from Q alpha. Why? Because in particular the coefficients are in Q, so they are surely in Q alpha. Okay, now what does this mean? So suppose let g of x denote the minimal polynomial. So let gx be the minimal polynomial of eta over Q alpha. Then g must divide this polynomial at least. Okay, and eta is the root of this polynomial, that much I know. Okay, so the minimal polynomial has to divide every other polynomial of which alpha is a root. Well, what does that mean? There aren't too many possibilities, right? This means that either gx has degree 1 or gx has degree 2. Right? So this means that either gx is linear, has degree 1 or 2. There are only these two possibilities. So if gx has degree 2, then it means it's just the same as this polynomial x square minus x plus 1. right? So that's more or less all we have to show, that gx can't be of degree 1. Okay, so observe, claim gx is not linear, cannot have degree 1. For if it did, then what would it mean? You know, it's a linear polynomial, and observe eta is a root of that polynomial. What it would mean is that the g of eta is 0 would just mean, and the fact that eta is linear and g is linear just means that eta would actually have to be in the field q alpha itself. Okay, so this is also because g is linear. So g eta is 0 and g is linear polynomial, right? Any root of a linear polynomial is in the base field itself. So this would mean that eta must have belonged to the base field q of alpha, but this is not possible. Why? Well, because q of alpha is a subset of the reals. Observe that alpha is the real root, right? It was the 6th root of 18, the real number. So this is a real number, but eta is definitely not real, right? Eta is e to the 2 pi I by 6. So if you wrote it out, it will have an imaginary part, right? Cosine of 60 degrees plus I sine 60 degrees, for example. Okay, so that's a contradiction. So this is a contradiction. Okay, so what does that mean? It just says that gx cannot have degree 2, which implies gx has, gx can't have degree 1, so gx has degree 2, which implies that it's just the same as the original polynomial itself. Okay. Well, what does that tell you? Well, that tells you that this is exactly the minimal polynomial. So therefore done. So therefore x square minus x plus 1 is in fact the minimal polynomial of eta even over a larger field q of alpha. See, a priori the minimal polynomial over a larger field only divides the minimal polynomial over a smaller field. But in this case, because somehow the degree is very small, it turns out that these two are the same. Okay, so what that means finally is that the degree of this extension q of eta, alpha comma eta, q of alpha is 2. Okay, and so we'll put these two things together, q of alpha eta, q alpha q. So we already showed that this extension had degree 6. We showed that this extension had degree 2, and the tower therefore has total degree 2 into 6, which is 12, by using this theorem on degrees of a tower of extensions. Okay.